This is managing complexity in the Halo 2 AI, or is it? My name is Damian Isla. I'm the AI engineer at Bungie. And I tell you, the main thing that gets me up in the mornings is the thought of building virtual brains. The thought of not just solving individual, maybe machine learning or planning problems, but sort of putting together the whole thing in this nice holistic way, solving everything from the sensor through perception to action and so on and so forth. So when I came to Bungie just over 3 years ago, I was a fresh-faced, starry-eyed grad student, and I came with lots of ideas about how brains should be built. I had what I thought were revolutionary ideas about, honest perception, knowledge representation. The idea that individual actors, individual agents in the world should have mental images internally kept of other objects in the world, and so on and so forth. And so I was ready to come to Bungie and just lay down the gauntlet and say, hey, this is how things should be done, and I will die on this hill. And so you can imagine my disappointment when I got there basically and found out that they were already doing everything I cared about. So I thought, well, damn, I'm going to have to come up with a new cause. And one of the things that occurred to me was that I don't remember really seeing in a game sort of context the issue of scalability ever addressed. So just the idea of what happens when we cram a brain so full of rules that it, do all those rules play nice together? How does it all work together? So I thought, well, here 3 years later, having addressed some of those issues, I thought I would give a talk called Managing Scalability in the Halo 2 AI. Now, that didn't end up being the title. Why? Well, because I was afraid I was going to get a lot of people thinking about this. How do I get 10,000 little orcs running around with their 3 states of attack, run away, and defend, or whatever it is? So, of course, what I'm really talking about is sort of building big brains. The idea that brains are, in themselves, maybe sort of communities of agents or communities of behaviors or something, and getting all of that to come together in a nice way. So, first question, I guess, to be addressed is just why scalable AI? Why are we interested in this at all? And the simple answer, I think, is more is better. The slightly less simple answer is that this is what I call the brute force approach to common sense. Just basically, the more unique situations you can react to, the more unique things you can do, the more specifically you can address certain problems in your world, the more commonsensical you appear to an observer. And while you can maybe say, well, that's a cop-out because you're not doing anything really smart, I would just say, well, if I'm a cop-out, so are these people who are basically addressing the same kind of problem and addressing it in the same sort of way in the knowledge representation domain. So, the Psych project is a project that's been going on for, at least 150 years down in Texas. OpenMind is a newer one that's sort of an online version of Psych, as far as I can tell. But the idea in both of these projects is about let's just fill a computer with all kinds of little common sense nuggets about the world. Because clearly the reason that computers can't talk to us or can't understand what we're doing is because they just don't have, some of that low-level stuff that we all know and we never even bothered to specifically learn or that we don't bother to teach because it's just so obvious. And I'm talking about stuff like, water gets stuff wet, birds fly, hitting something with a rock hurts, whatever. So I'm just arguing that there is an academic precedent for this kind of approach, and obviously we're not interested in doing this in a knowledge representation, sort of a factual way. We're interested in encoding behavior, so knowledge is behavior. For a game like Halo 2, I can see, no doubt there are more, but I can see at least, and I'm going to address in this talk, at least 3 different dimensions of scalability. And what I'm talking about there is volume, variety, and variation. Now, volume is what I was just talking about, just sort of what are all the things that I can do? For one of our actors, just sheer number of things that I can do, number of animations I can play, in this case, for example, number of vehicles I can drive. Do I know how to behave with vehicles, fighting vehicles? Can I shoot all these different kinds of weapons? Do I know how to then also do all the normal infantry-based behaviors and so on and so forth? So because of the introduction of things like vehicles and the different kinds of weapons, that becomes actually quite a difficult challenge. Because of course it's not just about driving the vehicle, it's about driving it well and also behaving with that vehicle in a different way. Obviously I drive a tank in a different way than I drive a little a ghost, sort of like a bicycle or something. On the variety side, I'm talking about sort of what are all the different kinds of characters and how do they differ from one to the other. So this is sort of an interesting kind of scalability. We have characters like the Grunt, who's one of our main, sort of workhorse characters that you see all over the game. You can have, minor variations, basically essentially cosmetic variations on the Grunt, like the Heretic Grunt, the same character with a different skin. You have other full characters that behave in very different ways with very different combat cycle, like the Flood, who don't have the sort of the usual fight, shoot at the player, hide, come out again when my shields are recharged. We even have things like Flood Swarms, which are swarms of tiny little guys that behave in a completely different way from everyone else and even perceive in a different way and so on. And then of course we have story characters as well, like Miranda, who you see over there. And speaking of story, that's one of the things that variation concerns itself with. So variation is the thought that, well, these guys, they behave and they also behave over time. So one character will behave differently in one part of the level than they will in the other part of the level. And why does that change? Well, the story can demand certain things at certain times for pacing, for drama, for a higher challenge at the end of the level or what have you. So if we're going to put together a brain that is going to be sort of generally competent, it also has to be able to be easily varied in all of these directions. So what is the ultimate goal with this? What are we trying to get here? Well, I'm a great lover of the theater, speaking of story, so I'm going to present my ultimate goal in plain manuscript form. The designer comes up to the AI engineer and says, I want X to do Y whenever Z. The engineer responds, okay, and I know exactly where to put that. And the designer says, I'm happy now, and he trundles back to his design bubble. So there's 2 points to that. 3. One point is that I get to make fun of designers all the time. The second point is that, maybe this is a very general point, but I like to point out that in a nice architecture and a great architecture, everything sort of has its nice place, and everything is sort of easy to do because you know exactly how to attack that problem, and there's already infrastructure there, hopefully, to address the kind of thing that they're talking about. But the most important point of this slide is that when a designer comes up and says X, Y, and Z, he's talking about a player experience. He's not talking about something smart. He's talking about when you kill one brute, the other brute attacks you. He's talking about when you cause this much damage in an elite, he has to take cover. He's talking about when I throw a grenade on a vehicle, the driver has to jump out. Lots and lots of these little rules that are in themselves very stupid, very, very simple. So that is going to be one of the main points of what we're going to be talking about, that in a lot of ways, we're not dealing with anything smart. We're not interested in something smart. And we're certainly not interested in AI that is sort of imaginative or can come up with novel solutions to problems that are unexpected and so on and so forth. If that kind of stuff happens, that's great. But the real point is that X, Y, and Z has to happen mechanically and predictably and every time. So what's the problem there? Why is that difficult? Well, it's difficult because there are a couple hundred of them. And, how do they interact is the question. So, a couple of requirements to our AI system. First one I'm going to call transparency. And this is about sort of the player's ability to look at an agent, or an actor, as we call them, and tell what's going on in the agent and the actor's brain. The point is that in order to make these rules that the player can learn to exploit, the player has to be able to look at a character and say, more or less, I think this is what's going to happen, or I think this is what he's going to do when I do this. So a lot of that is also about what we call facilitating the ongoing narrative in the player's head. So I run up to a grunt. I'm shooting him with a machine gun. The grunt is shooting back. I pull out an energy sword, and all of a sudden the grunt goes, ah, and turns around and runs around the corner. So I follow him around the corner with my energy sword. The grunt goes into the corner, finds he has nowhere to go, and turns around and starts shooting. And I say, wow, that was so cool, and I tell my friends about it. Now, the cool thing there is that there were two mechanical things that the grunt did. And hopefully I, as a player, will be able to tell my friend, hey, he totally ran away because I pulled out the energy sword. And he totally turned on and started fighting me again because he had nowhere to go. Now, those are two XYZs that a designer has told me. And I have, in essence, basically, told my own little story about what the grunt was doing. So I've attributed some kind of intentionality to his actions. What would be very not transparent, one might say opaque, is that would be if the grunt was just sort of acting randomly. That they were doing a bunch of different things, and it seemed sort of cool, but I didn't really get a sense that I was impacting the actor in any way. So, very related to the idea of transparency is the idea of coherence. Coherence, I sort of think is more of a temporal thing. Transparency is about making decisions. Then coherence is about the action over time. So, is the action that the actor is performing, is it focused? Does he seem to have the right priorities? When he gets interrupted, does he seem to get interrupted by something that is meaningfully interruptive? Does it make sense that he was doing one thing and now he's doing another thing? The ultimate in incoherence would be sort of the dithering problem, which a lot of AI programmers face throughout time. The idea that an actor might sit there and basically just twitch left and right because he can't decide whether to go get the weapon or hide around the corner. So that would be bad. Instead, we want nice focused action over time. And the other thing we want is directability. So, I mean, a big part of the Bungie philosophy is that really the designers came in all of this, and that however the AI behaves, they have to be able to take direction from a designer. The designer has to be able to impose some sort of maybe large scale rules as time goes on across the level, and impact behavior in some sort of way like that. So we have to make the AI receptive to designer input. And another general thing is that we have to make it workable for the AI engineer. So for me, or you. Basically, is the system just overall too complicated for me to use? Can I basically fit all of the workings in my brain at one time? And can I, reason about the system? And can I intelligently sort of query the system? And can I figure out what's wrong when it needs to be, when something needs to be debugged and so on? So we have all these things. Now, for these questions of transparency and coherence and so on, you should really check out talk from a couple years ago by Chris Butcher, my boss, and Jamie Griesmer, our lead level designer. That was a GDC 2002 talk, and that was called The Illusion of Intelligence, the Integration of AI and Level Design in Halo. That's an excellent talk, and it's a great philosophical overview and mostly a design overview of the role of AI in gameplay and so on and so forth. I'm not going to be talking about that. I'm going to be talking more about just how do we actually do the AI. So they had a nice little diagram in their talk in which perceptions came in from the world. It went through a little box with gears drawn in it, and then actions came out. And I was like, well, okay, fine. Today we're going to take that little box and blow it up. So maybe you get the idea from this slide that transparency, coherence, and directability, to some extent workability, all sort of center around the idea of decision making. Basically, are the right decisions being made? Are we making them over the correct amount of time? And are we choosing to be interrupted when appropriate, and so on and so forth? So really, I guess what I should be doing is inviting you to this talk, Scalable Decision Making in Halo 2 AI, because that's really what we're going to be doing. So when we think about the general problem of decision making, there's a bunch of things that go into it. Maybe most obviously is sort of perception, basically just what do I know about the world and how does that impact my decision making? The other question is memory. What have I been doing recently? What do I remember about things I've tried and failed to do, perhaps? More on the design side is sort of just the character definition. So a designer sits down and inputs maybe 500 floating point numbers which control behavior. And that clearly is not just a placebo. It is actually going to impact the behavior in some way or another. And then there's this question of level scripting. So again, like how does behavior change over the course of the level? Maybe not in an automatic way. In fact, certainly not in an automatic way. That would be really bad. What we're really talking about there is how the designer is able to change AI behavior in subtle and hopefully not so subtle ways over the course of the level because the drama requires it, because the pacing requires it, or whatever. So let's talk about decision making. Well, first of all, what are we going to be deciding between? Well, I'm going to call it, I'm sure we all have our own names for it, but I'm going to call it a behavior. Behavior as a program that takes temporary control of the actor in order to get something done. And the important thing is that behaviors are temporal. They're not just sort of single events. And this is, I think, one of the areas in which academic AI, things like reinforcement learning and so on, often sort of gloss over this point that an action is not like a discrete event. An action is, I got to do something and I have this much time to do it, or I recognize these ending conditions or whatever. Now, over the time that the behavior has control of the actor, they have these kinds of sort of action primitives. They can move the actor around to a particular point. They can orient, shoot, crouch, play dialogue. And they can also trigger what I'm calling actions, which are things like get into a vehicle, lean up against a wall, throw a grenade, so on and so forth. Very basic stuff. And then, again, like behaviors have a notion not only of duration, but also of relevancy. So they have an idea of like, well, when is it appropriate for me to turn on? Another way of saying that is starting and ending conditions. So we have a bunch of them in Halo 2. We have things like fight, vehicle entry, throw a grenade, cover friend, check body, which are post-combat behaviors. There's also really specific stuff like elites can walk around and wake up a sleeping grunt. We're going to have to be able to do custom stuff like that. And in Halo 2, we had about 130 of these different things. Any particular character probably have less, probably have maybe 80 for one of the workhorses. And so this is how it all sort of fits in, and this is the absolute canonical structure, so hopefully we don't need to explain too much about it. Things come down from the world through perception and through the knowledge model. We build a couple of target possibilities. We pick a target, and then we choose a behavior somehow, and then those sort of control streams come out of that and impact my body or whatever. So how do we actually, what is that decision process? Like, what is going on in there? Well, if you ask a designer, he's going to say something about the combat cycle probably, or at least if you ask a Bungie designer. And this is just basically the sort of canonical set of states that an AI can go through. Idle, he sees something, he goes to combat, he loses track of it, he goes to search, he sees him again, he goes to combat, self-preservation, flight, and so on and so forth. So again, that's very experiential. The player is going to see hopefully very, very explicitly all of these different modes of behavior. But of course, there's tons and tons of complexity hidden in there. Namely, when do these things happen? How long do I self-preserve for? When I flee, do I ever come out of it again? How do I search? So on and so forth. So this is not a decision mechanism. This is just sort of a high-level description. This is a decision mechanism, behavior tree, and here I have to apologize for the AI programmers in the room because this will be the 30 billionth time that you've ever heard a behavior tree explained. Each of these boxes represents some kind of decision process, and as I choose one behavior, its children then become candidates for expression and so on and so forth. So I start with the root. I have only one choice, so I go that. I decide, well, now I have 4 high-level behaviors to choose from. Well, I choose engage. Now I have these options. I decide search because I can't see the guy. And then I decide what kind of search, and it's uncovered. So very simple. Here I'll get a little polemical. I mean, like, one of the problems I think we have in the game industry is that we tend to reinvent the wheel over and over and over again. And in particular, hierarchical decision structures is something that everyone is using and everyone's calling by a different name. So I apologize for spending any time whatsoever on it. But But as it is the fundamental decision structure of the Halo 2 AI, I have to deal with it in some way or another. So we all know the good things about it. Sort of an intuitive way to think about decision making. It's fairly modular, and it's nicely scalable because I'm branching a tree and I don't have to think about all the other branches when I'm down one particular branch. The bad thing is, of course, that it's never really that simple. Though I've implied all kinds of modularity and encapsulation and so on, there is all kinds of subtle communication going on under the hood that we can't really get rid of. Debugging is hard, often because we're not debugging in terms of why did a guy do something, but why did he not do what I expected him to? Sort of negative debugging. And also memory is hard. And I'm going to talk a lot more about memory later on. So I'm going to do my absolute best to sort of stick to what is actually, I think, sort of unique about our behavior tree and why we made certain decisions. Well, first of all, the first thing to say is, well, what is actually going on inside those boxes? Like, what kind of decision routine are we using? Two general approaches. You could say, well, the parent knows what kind of children are attached to it, and so just explicitly says who gets to run, which is fine. That kind of works. Gets a little more hairy when we get to something like 20 or 30 children, which we have in some cases in Halo 2, because you have to come up with decision logic, which handles all of those cases. And it's also not very easy to sort of pull behaviors in and out of it. So, the parent, the custom decision routine has to take that into account in some way. So we generally go when we can for the sort of a child competitive model. Even within the child competitive strategies, though, you could sort of think of two large-scale approaches, sort of the analog relevancy approach. And I've dealt with a lot of academic systems which have done it this way. Basically, each behavior provides some floating point number, which is how much I want to run. And then the parent says, okay, I picked the one with the highest number. And I probably give a boost to the guy who was running last time because I don't want to dither or something like that. That's good. That's good if you like subtlety, which as an industry and as a company we do not at all like. And in general, if we were using an analog relevancy, we would generally want sort of discrete events to snap on authoritatively, and so we'd probably go from 0 relevancy to 5,000.0 relevancy from one tick to the next. But as long as we're doing that, well, why not just go ahead and do a binary relevancy? So in other words, each behavior is just saying, yeah, I want to run or I don't. So once I have that, I have a couple of options open to me about how exactly my decision is going to go about. There's things like the prioritized list. So my list of children is prioritized. I pick the first one that is relevant, and on subsequent ticks, more relevant guys can, or more higher priority guys can interrupt lower priority guys. There's things like you can do it sequentially. You can do it sequentially looping. So I go back to the beginning when I'm finished, and search is an example of a subsystem that uses that scheme. Randomized and things like one-off randomized, which is what our post-combat uses. So post-combat has a couple of behaviors available to it and gets to run each one once at most. But it will probably turn off before it gets to it. So the question of well, what should we use then? Should we use parent custom? Should we use analog relevancy or use binary relevancy? The correct answer, of course, is that we should use all of them. Because they're all going to be useful at one point or another. So this is something maybe silly, but it's something I'm going to be doing across the talk. I have about 5 design principles scattered throughout there. And these are actually pretty, I think, guiding philosophies to the way, at least, that I design systems and certainly AI systems. Yeah. So it turns out that the prioritized list approach is actually going to be the one that we use by far the most. In fact, on many of the high-level behaviors, those big groups like the root group or the engage group or whatever, the prioritized list is actually really important, and we end up using it that way, which is kind of satisfying because in a lot of ways, that's also again the way that you approach a problem, right? You say, hey, I have a problem. Can I do the best thing? No. Can I do the second best thing? No. Can I do the third best thing? Oh yeah, I can. Okay, great. So anyway. But there's a problem with prioritized list approach. What happens when the priority is not constant? And I'll give you a good example. I hope you can read that. Those are three behaviors in that little behavior group there on the right: charge, fight, and vehicle entry in that order. And guys basically say, hey, when I know there are enemies around and I see a vehicle next to me, I want to get in the vehicle because that's a smart thing to do. However, if I'm actively fighting a guy, then I don't want to do that. I want to concentrate on the guy, and then afterwards I'll go into the vehicle. So a designer has said, yeah, that's a good rule to have. Unless the player is in the vehicle, in which case you absolutely want to get in the vehicle no matter what. In other words, the priorities of the vehicle entry and the fight behavior are switched. So, well, how do we do that? There's a good example of two XYZs which are sort of conflicting each other. Well, the way we do that is we introduce this idea of an impulse. And an impulse is sort of this, it's a free-floating trigger. It's just something which is, it's basically taking a alternative condition to a existing behavior, and it's moving it out into a different place. So in this case, we solve the problem by basically creating a player vehicle entry impulse, which is higher priority than fight, and but the general case of vehicle entry is still lower priority. So impulses in some way reference some other behavior. And there's two ways we can go about executing them. We can do in place. So in this case, it would be something like I'm running engage and I'm running fight underneath it, and my player vehicle entry impulse becomes relevant. And as a consequence, I begin running the vehicle entry behavior at the priority level of the original impulse. And the other option is to do sort of a redirection. In this case, I've added a self-preserve on damage impulse, which is just above the fight. And what happens now is that when that becomes relevant, I can actually redirect my execution stack to go to another part of the tree. So that's just a generally useful thing, and that's in fact how we do a lot of our self-preservation triggers, because as you might imagine, there's lots of reasons, all of them different, to actually take cover. So that's, I think, another design principle, which is basically formalize complexity, don't hide it. Hiding it in this case is the very strong temptation to just say, hey, these two things trigger the same behavior, so why not just put it together in one relevancy function and be done with it? In fact, it's really worth separating those two out into two different sort of system-recognized entities so that we can assign them different priorities and for other reasons too, which I'll get into a little later on. Just very quickly, there's another reason to have impulses around. Imagine an impulse which doesn't reference another behavior at all, which is just a piece of code, and I've just stuck it into the tree somewhere, and I never actually cause it to become relevant or anything. I call those hacks. Or, to put it nicely, localized code with ad hoc functionality. And as stupid as that sounds, it's actually a really good idea in my mind to basically never let the architecture get in the way of doing something simple. If I can write a little piece of code which says, hey, when I recognize these conditions, play this line of dialogue, then I should just be able to do that. And the nice thing is that an impulse is just a little chunk of code, and I can put it in the tree, and it runs in a very specific place under specific conditions. So we have actually two examples right there, but we have a ton of examples of where we do that kind of stuff in the Halo 2 AI. Crouch on danger impulse is something that sits at the top of the engage behavior group, which says basically, hey, when my danger level gets above a certain threshold, then I crouch down. So continue what you're doing, whatever other behaviors you're running in this group, but crouch down while you do it. That's cool. The other thing is a dive impulse, where a dive is sort of an instantaneous action. It's just sort of launching of an animation. So if I can detect the conditions that should cause me to dive, then there's really no reason for me to continue doing that over time. I can just instead have a little piece of code that says, hey, dive, and then the guy does it. And then presumably he has some ability also to analyze his own body on subsequent takes and decide, hey, my body is being used for this animation. So I actually think that's important to put into design principle 3, embrace the hackery. That's the great thing, right? There are two things that are demanded. When we want to do a hack, there are two things that are demanded of our architecture. One is let us do it, and two is help us to contain, catalog, and otherwise keep track of it. And actually, this fulfills those requirements pretty well. If only because in order to create an impulse, we have to add it to this long global list of impulses, and so it's pretty hard to forget about it because it's there whenever we look at it. Here's another problem. In determining relevancy, we check the same conditions over and over and over and over and over again. And I'm talking about things like the actor's vehicle status. Certain behaviors he can run when he's in infantry mode, others he can run when he's a driver, other when he's a passenger. And almost every behavior has some requirements in terms of vehicle status. So every behavior has to go through and say, hey, are you this or are you that? Are you one of these? Are you this one in particular? Are you one of these two? So on and so forth. Another example is the actor's alert status. Is he idle in combat? Does he have a visible target? That kind of thing. So that's kind of dissatisfying. The way that we get around that is we attach a little piece of metadata to each behavior. What that does, first of all, is that it forces each behavior to declare its execution conditions, which is not a bad thing because it forces us to think, hey, actually, should we allow this behavior to run? Does it make sense for a passenger in a vehicle to do this? Or only a driver, so on and so forth. In Halo 2, those conditions were expressed in just this little bit vector, and so it was really nice and easy to say, hey, do my actual state bit vector match up with this conditions bit vector for this behavior? So I know what you're thinking. You're thinking, well, that's pretty stupid. That's just a way of optimizing a decision process, right? That's just a way of really quickly of checking a bunch of conditions. And of course, that's true. But in fact, I think there's sort of an interesting interpretation alternatively, and that's that metadata sort of acts as a behavior mask. Basically, what you see on the left here is the behavior tree as it looks like for a infantryman. The one in the middle is the driver, and the one on the right is the passenger. So you see that what we're sort of doing is actually filtering out major chunks of the tree as we go through and change our overall body posture, our overall state. And I think that's pretty powerful because, well, first of all, clearly, the fewer decisions we have to make, the better. The fewer options that we have at any point, the better. And it just forces us to think, well, what is actually the structure of the decision-making process at any particular time? So that's actually a useful thing for us to do. Here's another problem. Character type specific behaviors. So basically, grunts have certain things that they can do. So I want to put it into the tree. But at least we'll never, ever be able to do that. So why do we actually go to the trouble of forcing the lead to go and check that relevancy function? Even if that relevancy function immediately fails, because maybe at the top of that relevancy function it says, if you are a grunt, then consider. Another example here, well, one of the examples is the retreat from scary enemy impulse. Grunts have a lot of retreat behaviors, so there are a lot of retreat conditions. So basically they have a lot of impulses, which are sort of retreat on this, retreat on that, retreat on the other thing. But a lot of other characters never need to consider it. So the solution is, again, to attach custom behaviors to the tree. In this case, this is sort of a generic fragment of the tree, and this is what it would look like for a grunt. So we've just taken a bunch of impulses and we've added it in a custom way for the grunt, and that's a way that we can make sure that it's only the grunts that consider doing those things and not other characters. What's interesting about that, and what's also sort of interesting about the previous example, is that all of a sudden we're starting to see that the tree is not this completely static structure, that we actually can sort of tweak it in runtime. It's sort of plastic in these ways that we hadn't maybe thought of before. I think this is also important because it's sort of it's design principle 4, so of course it's important. It's a variation from a stable base. So you can sort of consider the generic tree that you see on the left here. Maybe that is actually the thing that implements that designer diagram at the beginning of the combat cycle. So maybe like some of the basic structure of our brains that we're considering is encoded in the generic structure. And so then other characters can come along and add different trigger conditions and different transition conditions and so on. So The alternative would, of course, be to say, well, I'm just going to completely rebuild a new tree for the grunt, and this will be the grunt tree, and then the elite will use the elite tree, and so on and so forth. But given how actually complicated our brains are, there's going to be a lot of repeated structure, and so a lot of common work that could be combined. And so I think by doing sort of the custom behavior approach, we can actually avoid a lot of that. Here's one more thing. Rare event-driven behaviors are tested for every check. Take the behavior which they talked a lot about in the talk a couple years ago. The grunts flee when their leader dies. So a bunch of grunts are fighting with their elite beside them. You headshot the elite, he goes down. And what should happen is that all the grunts should throw up their arms and go running away. Yet another retreat behavior. What's dissatisfying, though, is that if we put it just in a tree as usual, what's going to happen is that we're going to go every single tick and we're going to say, hey, did my leader die? No. Did my leader die? No. Did my leader die? And so that's sort of a waste of time, more or less. And it's also, well, in my mind, it's also a waste of mental bandwidth. So we're going to do something we call stimulus behaviors. And these are behaviors or impulses, I should say, that are dynamically and asynchronously placed into a tree at a specified location. So how does that work? Well, I have my actor, and he's got his decision structure in there. And I have events coming in from the world. For example, I have an actor died event, which comes in. My stimulus system turns that into which you absolutely cannot read there, but it's a leader dead retreat impulse. And it's also specifying a duration for that impulse. So basically we're saying a lifetime, like how long should that stay in my tree? Because it just makes no sense to have the guy go down and then 5 seconds later actually, go running away. So it's an indication of how long we should consider reacting to the thing. Well, immediately that becomes active because the thing maybe just did happen. And it was put in because it just happened, but it became active because I'm a grunt and I do those things. And it's an impulse. And so what happens is that it redirects us to the retreat behavior, and off I go, essentially. So, well, why am I actually making it so complicated? Why not just say, hey, when the stimulus system gets that event, just start doing the damn thing, just start fleeing. Well, sure, okay, we could do that, but maybe that's just one XYZ. In fact, it is just one XYZ. And there's another XYZ which says, if the player comes up in a vehicle, driving a vehicle, you absolutely get in, no questions asked. There's nothing that is more important than getting in that damn vehicle when the player drives up. Well, in that case, we have to be able to refuse to flee under certain circumstances. And it's that priority that the tree actually captures for us. So it's sort of the thought that anytime we're making decisions outside of the tree, it's not necessarily a well thought out decision. If it's in the tree, it is. So there we are. Very quickly, we also support sort of a joint behavior mechanism. We do it through invitation. Basically, guy one on the left says, he comes to some behavior which says, hey, invite these other guys to do this thing with me. At some other point, the guy on the right, guy two, gets the invitation, perhaps through a different behavior, and accepts it, and he says, yeah, sure, I'll do that with you. And at that point, they can set up some kind of shared memory space and do all that stuff. That's cool. That's cool for things like, say, vehicle flipping. I don't know if anyone has ever seen it in the shipping game, but if there are 3 Marines driving along in a Warthog and the Warthog flips over, they'll actually get together, set up a joint behavior, run around to the same side, and they'll all push the thing over together, and they'll get back in, which is cool. In that kind of problem, invitation-based joint behavior actually works really well, because it's sort of like, I don't even want to try to do this thing if I can't get my other 2 friends with me. Another alternative means of setting up that kind of thing is sort of a blackboard approach, and that's also good for other problems, particularly the kinds of problems where I'm going to be doing something, and if you guys want to join me, come along at any time. Of course, design principle 1 says we should be doing both of them. And had we had a couple months more, we probably would have done both of them. But anyway, there's a behavior summary. A couple of what I think are sort of cool features to our behavior tree. The behavior DAG. Actually, I didn't even mention that. It's sort of a DAG more than a tree because certain behaviors can appear in more than one place. The fact that we use binary decisions, the use of impulses, metadata, custom behavior stimulus, so on and so forth. I think the most important thing to take out of all of this is that actually the tree is sort of fundamentally dynamic structure now. Like we're adding stuff to, we're taking stuff away, we're filtering out entire branches and so on and so forth. And that's really flexible. That really makes it a lot easier to work with and a lot easier to put new stuff into it and just have it all work. So I don't have a lot of time left, actually. I'm going to talk a little bit about memory, though. Because memory is actually a fundamental problem of behavior trees. In the ideal world, what would we do? We would just say, hey, each behavior in every single actor gets a little chunk of memory and gets to do whatever they want with them. Unfortunately, that's a lot of data to keep around, especially if we have hundreds and hundreds of behaviors. So what do we do? Well, let's do the obvious thing, and everybody does this, right? Let's keep around state only for the behaviors that are running. Whatever. In Halo 2, that was a very explicit sort of layer allocation. We had a chunk of memory. It was divided into layers. The behavior running in layer 1 got to do one thing, or got to use the first chunk, layer 2, the second chunk, and so on and so forth. Which is fine, except of course we lose that information every time we switch behaviors. So what do we do about that? What do we do about state that we need to keep around regardless of whether we're running behavior or not? An example of that is the grenade throw, right? I'm not running a grenade throw all the time, but I do have to remember when the last time I did throw a grenade was, because a designer has said, grenades can only be thrown every 5 seconds and not more. Well, my answer to that is just that memory is actually a pretty complicated thing, and there's actually a couple ways in which we store memory in the Halo 2 AI. First is what I've just talked about, behavior state. It's sort of a short-term thing, like what is the data that I need to successfully complete the behavior that I'm running right now. The other thing is persistent per behavior. So in other words, I have a chunk of memory in the actor, and we let individual behaviors store small amounts of data when they absolutely need to in that memory chunk, and that works for things like grenade throw. We also, however, have to think about doing it per target. What about a melee, for example, where I'm only allowed to melee the same guy once within every 5 seconds? But just because I meleeed one guy doesn't mean I can't melee another guy. So clearly at that point, I can't keep global state in my brain about meleeing in general. I have to actually store information per target. And so that's another thing that we do. We have a name for these objects because they're always being deleted and created as appropriate. We call them props for no other really good reason than we call the agents actors, and so the actors use props. Sure. It's completely inappropriate in every other way, but in that way it's good. And something that I'll just mention is that props for us are also perception caches. So in other words, I'm getting a stream of data about objects in the world, and we're storing it in that same structure. And they also pretty much constitute our knowledge model. They basically keep track of, basically that is where I keep track of things in the world. So it's sort of interesting to me that our knowledge model really consists of two parts. It's, first of all, what I'm sensing and what I remember about what the object is doing. And it's also the things that I've done to the object, or the things that I've tried to do to the object. As fast as I can, I'll do the example of search, because search is an example where we have to keep per target information. And hopefully this will illustrate pretty clearly why. I acquire a certain target, I fight it, and after a time it takes cover. So of course I decide to search, because that's what I do when I lose my target. In the course of searching, because it's an action that takes duration, in the course of searching I inspect the last known location for the guy, and I select a new search point. Maybe that's in the direction that I last saw him heading in. As I'm on my way over there, I acquire a second target. In deciding to fight the second target, because now I have a more immediate problem, I deactivate my search, and any sort of short-term memory that I had about my search is actually discarded. I kill target 2 in short order, and I switch back to target 1. Still not seeing target 1, I decide to search for it, and now the question is, well, where do I search? If I had stored that in the behavior state in that short-term volatile memory, I'd be in big trouble because I'd be starting again essentially. Luckily, we put it instead in the per target behavior, and we can use the existing search point. So I think that's a cool example. First of all, because it's a really coherent, I think, sequence of actions that our agent takes. A player watching this, I think, would pretty well understand that he sees a guy going after a target, gets interrupted by something else. Once he's dealt with that, he continues on what he was doing. So I think that's cool. And I think the other cool thing is that what it sort of suggests is that things like search location is really more a property of my mental image of the target, more so than a property of the search behavior itself. What that means is that it's pretty useful when we can to put stuff in the knowledge model rather than keep it in the behavior state. And I think all of this approach to memory in general also constitutes another example of design principle 2 about formalizing complexity and don't hide it. Hiding it in this case would have meant trying to make do with one type of memory, or even worse, it would have meant trying to make do with that short-term volatile memory. Instead, we've noticed that there's going to be these different ways in which we use memory, and so we're going to very explicitly formalize this is what this memory is used for, this one is used for, and so on. And so every time I come to store a piece of data, store a variable, I have to really think about, well, what do I want the persistence of this data to be? And let me put it in the appropriate place. I also like it because it lets me use terms like short-term memory, thereby implying that we do anything, basically appropriating a psychological term and thereby implying that we're doing something like what's going on in our own brains, which is, of course, nonsense. So in the last 15 minutes of the talk, I'm going to talk about how designers deal with our AI. As the diagram suggests, there's two general parts to this problem. The character definition, which is about what are the static properties of the character. First of all, things like model, what model, geometric model do they use, what animation graph do they use. And we also have behavior parameters. So like what are the set of floats that control my, all my flee thresholds and my fights, and my combat ranges, and how I use certain vehicles and so on and so forth. And this is static control because it's basically a static definition that we're going to load into all these different situations, and it should, hopefully that definition will cover every problem we're going to come across. And then there's level scripting or dynamic control. So again, like how are things going to change over the course of the level. You'll note, of course, that the first part deals primarily with the problem of variety. So again, variety is the fact that we're going to have a bunch of different types of characters. So we express those different types of characters through different character definitions. And the other part deals specifically with variation. Again, how behavior changes over time. So looking at the way that we deal with variety, in Halo 2 we have a certain number of character types, I think 16 different character types, and those are sort of high level. These are elites, they're grunts, marines, hunters, the big guys with the shields, and so on and so forth. And then for each one of those character types, you can have what we call variants. So you're not just an elite, you'll be a gold elite, a red elite, an honor guard elite, jetpack elite, so on and so forth. And each variant is a different kind of character and gets its own .character definition file. Here's the problem. If we have 64 variants, which we actually do, about 80 behaviors per variant, and about 3 parameters to control the behavior correctly per behavior, we have up to 15,000 different floating point numbers that we need to author and maintain, which is a pretty untenable situation. Luckily, we have a way to deal with this. And that is that character files are not just flat lists of parameters, they're actually divided into blocks. So I'll have a vitality block, which says how much life I have, how much shield I have, perception block, search block, weapon usage block for each different kind of weapon. In a character file, each of those blocks can be instantiated or not. And we're going to put them in a hierarchy so that child characters only instantiate significant variations from its parent. And at the root of the tree, we have something called the generic character, which gives reasonable values for all the parameters that we could possibly want. And so what we get is a character tree. And again, the nice thing about that is that when I come to decide, hey, I know I want to create an aggressive jetpack elite, which is going to differ from the jetpack elite in the following ways. When I come to tuning that character, I can just focus on what makes that character particularly special with relative to its parent. So that's a pretty useful thing, and we have quite a fleshed out character hierarchy in Halo 2. This is, of course, another example of design principle 4 in action, variation from a stable base. The other thing that characters reference are these things that we call styles. And styles are cool, as it said, because they're basically a behavior mask. What you see is one of the sort of a screenshot from one of our tools. And what we basically have is a long, flat list of all the behaviors that we could possibly be interested in. And what that lets us do is basically expose to the designer when certain impulses or behaviors are available to particular characters. So maybe I have a grunt that should not flee under any circumstances for some reason. It's a zealot grunt, which instead always charges the player in a suicidal way. Well, that's very easy to set up because we can just go through that behavior list and say, hey, you can't retreat, you can't self-preserve, you can't do anything. And hopefully that'll just all work. The other thing that styles do is they are able to bias control parameters. And I'm not going to talk about how that works because that's I'm already almost out of time. But there is a way basically so that we can indicate basically I want to use a more aggressive parameter set, I want to use a more defensive parameter set, and so on. And the other important thing is that styles are superposable, so I should be able to combine styles in various ways, and I'll explain why that is important in a minute. Note again that this is another reason why impulses are a really great thing, because by separating out different triggers, even though they're referencing the same behavior, if I separate out into multiple impulses, then I'm actually exposing that to the designer to decide whether or not it should be included in a particular character. So I think that's all cool. In terms of dynamic control, so now we're talking about, well, okay, how do we actually go about scripting at a high level behavior? In Halo 1, we did it through these things called encounters. Encounters were groups of actors combined with a group of areas that those actors could occupy. And when fighting was done in one area, they were moved to another encounter. One of the problems was that moving actors from one encounter to the next was sort of architecturally discouraged. It was kind of difficult to round up your actors and make sure they all got through to the next encounter. So in Halo 2, we organized it a little bit differently. We said that actors are collected in groups called squads. We have zones, which are groups of areas, and we have something else called an order, which is sort of a mapping between the two. So the inspiration for the order structure is sort of, well, it's the very kind of order that a sergeant might give his grunts, his men. Basically orders that are barked in the midst of combat that are sort of like, take that hill or hole up in that bunker. Or put in a more generic form, occupy this space and behave this way. So there are two parts of that. There's the position direction and the behavior direction. So position direction I won't go into too much, except to say that here's a battlefield, say, there's enemies standing up, presumably towards the top of the screen. And so the way that a designer might approach this is by saying, well, you're going to start in this initial order, and you're going to occupy this space, and that's an area that they can define by using essentially point clouds. And they're going to say, well, you can occupy this space and basically do whatever you want within this area. Now, certain trigger conditions, certain conditions might be met. The designer may be scripting a certain order transition or so on, but at some later point, the order 4 will be assigned to a particular squad, and soon they'll be given a new space to occupy, and so on and so forth. So we have a mechanism actually to do automatic transitions between orders, and in other cases, those are explicitly scripted. Now, in terms of behavior direction for orders, there's a couple of things that we can do. There's certain sort of directions that we can include in the order. The first is, well, vehicles can be disabled or enabled. So I check the box, and suddenly none of the actors in that order are allowed to use vehicles. I can ask the actors to turn on or off active camouflage. I can tell them to follow the play or not. And I can also give instructions on rules of engagement. So, hold back and don't fire until the player opens fire or until you're fired upon. And the other thing is that we, again, have a style. So, again, the style is behavior mask and is also a control parameter bias. So that basically allows me to say, hey, you're going to do this, you're going to occupy this space and you're going to do it aggressively, or you're going to do it in a harassing way or in a cowardly way. And so that's just another knob that is available for the designers to tweak. That's a little bit dangerous because styles can be, styles are very clearly sort of the sledgehammer approach to behavior. So it's very possible for a designer, unattended, to create a style that actually leaves the actor with nothing to do. And so that's a danger. The two good sides of that is that I personally am always in oversight of those style files. And the other good thing is that we only need a very few of them. Again, we're not that interested in subtlety, so beyond attacking and defending and sort of neutral, there's not necessarily a lot of other alternatives that we necessarily want to have available because the players simply won't recognize them, won't appreciate them. But you see that using these different kind of knobs that we're providing through the order, we can put together orders which say things like, all right, men, engage active camouflage and move forward cautiously and don't open fire until the chief does. So that's kind of cool. What it means is that we actually have some sort of, quite an expressive language to actually control our actors and move them around the level in a particular way that serves the drama or the pacing or whatever. The especially good thing is that there's no scripting involved in this. This is all through a GUI. And so they never have to actually touch a text processor. So in summary, this is sort of the various control structures that the designers have at their disposition. The actor has a behavior tree in his brain. He's a member of a squad. The squad is assigned an order, and the order references both a set of areas and a style. At the same time, the character also references a character definition, which also feeds behavior parameters into the tree and also provides a style. So again, you'll see the two styles on the right there, and that's exactly why you need the styles to be superposable, because in fact, you're going to be combining them from different sources. In fact, if I'm sitting in a vehicle, the vehicle is also going to have a style for that particular seat, because in certain situations, I don't want a tank to behave the same way as something else. Or I don't want to drive the tank the same way I might drive a warthog. I don't want to strafe on my target, say, or what have you. So that's cool, and I think it's cool, in fact, enough to call it Design Principle 5, which is just work with your representations, and even more importantly, make sure your representations work well together. The thing I like about all of this is that all of the structures that we're looking at here, they all feed back into the behavior tree, ultimately. And the nice thing is that they also feed back in principled ways. There's very little that's ad hoc in this system. So I'm at the very end. I have quick recap. These are the design principles. Always choose D, all of the above. Formalize complexity, don't hide it. You want to embrace the hackery always. Variation from a stable base is useful. And you always want to work with your representation, make sure you're leveraging their strengths. In terms of technical takeaways, I'm hoping at least that some of the things that we talked about here are actually also useful to you guys who have built similar systems. To me, the technical takeaways of the talk should hopefully be the idea of the dynamic behavior tree, so a tree that's not just static. The idea of binary relevancy as something that's much simpler to get, very, very specific priorities implemented. The idea of behavior masking, either by style or by metadata. We use a principled approach to memory. And lastly, as hopefully illustrated by that example with search, whenever we can, we take the smarts out of the behavior and we put it in the knowledge model. Conclusions, I just have two quick conclusions. First of all systems, as we've just said, need to play ball with the core decision mechanism. If decisions are going to get made, if behavior is going to be impacted, it has to be in some way through that decision tree. Sorry, behavior tree. Decision trees or something else. And the most important thing, again, is that we're not looking for a smart architecture in a lot of ways. We're looking for an expressive architecture. Because after all, what's important is the designer and his XYZ. So that's what I got. Thanks. Do we have any time for questions, or just a few questions? If people could walk up to the microphone, if they can get them. And also, yes, if you please sign up fill out those evaluation sheets. No questions at all.
Actually, I just had a quick question. I was wondering how much it would have complicated your job, if particularly with dealing with short-term memory, if the characters, the enemies had ran out of ammo.
Ran out of ammo and then presumably had to go pick up other weapons.
Yeah.
Actually, our designers have design objections to that kind of thing. One of the things they talk about is that a character with a certain weapon has a very specific function. So a jackal with a sniper rifle has a certain function in the encounter. And then, in fact, by allowing the jackal to change weapons, you're actually making this whole system less predictable for the player. And you're basically invalidating for no good reason the player's plan that the player is forming to attack a certain encounter and so on. So for that reason, we don't generally like the idea of AIs. Maybe your allies can do it. That would be one thing. But we don't generally like the idea of enemy AIs changing weapons. And obviously, if they're running out of ammo, then that doesn't leave them much to do, which sucks. So.
I guess there's the cheat that you can be down to one ammo, give it to an ally, and then run around, get stuff, and then come back and he's been firing with it, but it still only has one ammo.
Yeah, no, that's not a bug. That's a design feature. Yeah. Well, what it also means is that it's this really cool thing where, contrary to what your intuition may be, whenever you get a really cool weapon, first thing you should do is give it to the AI.
Right.
Yeah. Go replay Earth City, everyone, with that in mind. Give the AI the rocket launcher.
Hey, I have a question. Do you have any system that lie down between behavior system and animations, or you play an animation directly from behavior system, or both of them?
Is the animation system different from the behavior system?
No, do you have any another system which might be lie down between behavior and animations?
One thing I didn't talk about is sort of the low-level animation and movement and shooting control layer, which is a whole other huge system, which is basically taking these very high-level instructions from the AI, things like take a path to that object or take a path to that point, and is actually doing the sort of the low-level navigation and steering and that kind of thing. So there is a whole mess of complexity down in that layer as well. Yeah. Does that answer your question pretty much? Or either way.
Well, I made a question. I'm not sure I understand correctly. Is there just one brain for everybody, kind of like reaction code? Or is it a separate copy of the tree, the efficiency for each actor?
There is the question was, if I got it right, is there a different copy of the tree for each actor, or is there some kind of shared structure? The answer is that in fact each actor ultimately, each type of actor, not every actor, but each actor class has a static tree definition assigned for that actor class. So we'll have exactly 16 of them in the game for each character type, elites, grunts, and so on.
When you maybe insert a temporary part of the tree, that's just for that one class.
No, well, when I'm inserting for the stimulus behaviors, when I'm inserting a behavior into that tree, that's actually for one particular actor. Okay, not for a character class.
The leader die can insert it into every grunt's tree.
Yeah, well, but you don't want to do it. I mean, if you want to do it for every grunt, then it would be a good plan to do it for the character class. In fact, we only want the grunts that are part of that leader's immediate area to actually undergo that. And in a lot of cases, it will be very specific individuals that you actually want to run a particular, that you want to stimulate in that way. So,
I was wondering how the decision tree is represented. Is that something that's done in code, or do you have a separate data file for that?
the behavior tree, that's done through just hard coded. Yeah, that's all encoded.
Thanks.
The only sort of data driven aspect of it is what is allowed by particular characters. So again, that style.
When the player dies, are there any special considerations for resetting the trees?
Is there any special
Considerations for resetting the trees?
resetting them?
Yeah, back to the...
Well, no, we have a whole game state system that takes care of restoring exactly state. You're talking about just the player dies and we restore it to. There's actually no need to do that because the static structures are just that. They're static. The static, that just define the structure of the behavior trees themselves. And then the character's place in that tree is just defined by its internal state. And that state is part of a game state system, which is just wholesale sort of plopped in and plopped out as we reset and save.
I was just going to ask about debugging this, and if you had any debugging tools. Like, could you actually look at a behavior tree of a character, like the instantiated version of it?
Yeah, that's a really good question. We actually do not, and we do not have the ability to say, hey, show me what a grunt tree looks like, and that's a glaring deficiency. Like we would have to do that. We should do that. That's a good idea.
How was debugging it? Like, if I can imagine they applied a mask onto it, and there's a bunch of different objects in there all playing into the one tree, it might be really difficult to. Like, I can see how easy a designer would be able to rack a behavior.
Sure. Yeah, and it happens all the time. In fact, they shouldn't be left alone with it. I mean, the most useful debugging tools that we had was just the ability to print out each actor's behavior stack as they run around the world, and also the ability to print out basically the decisions that they're making. So basically, how they got to their current place in the stack. So, but you're right that that doesn't help us with the problem of why did he fail to run this other behavior.
How do you introduce randomness? For example, if you don't want your actor to always throw a grenade every 5 seconds, but grenade is highest on the list, how do you introduce some randomness? Between picking.
Well, again, it's sort of a relevancy thing, right? The behavior can declare itself relevant or not, which just means that in the relevancy function itself, it can do any kind of probabilistic test it wants to. So. All right. Thanks, everybody.